The RegionGen framework addresses the modifiable areal unit problem, MAUP, in spatial data management for spatiotemporal transportation service management. This novel data-driven region generation framework formulates region generation as a multi-objective optimization problem, aiming to create regions with good spatial semantic meaning and predictability. To achieve this, the authors first segment a city into atomic spatial elements based on road networks and obstacles. These elements are then clustered into regions by maximizing various operation characteristics, such as ride-sharing and freight transport services. This clustering process is modeled as a multi-objective optimization problem, which is solved using a proposed multi-objective co-optimization algorithm. Extensive experiments have been conducted to evaluate the RegionGen framework, demonstrating its ability to generate more suitable regions than traditional methods for spatiotemporal service management. The implications of this framework are significant, with potential to improve the efficiency and effectiveness of online transportation platforms. In the realm of spatiotemporal data management, the current industry practice for region specification is predominantly ad hoc and manually defined, often employing fixed shapes such as grids or hexagons. This approach can result in unpredictable and unforeseen effects on the operations of spatiotemporal services. Conversely, an optimized region specification can significantly reduce the prediction error for spatiotemporal service demand by approximately 10%. The authors contend that region specification is a pivotal yet largely under-investigated issue. They propose a unified region generation framework, dubbed RegionGen, which facilitates the adaptive formation of regions for various spatiotemporal transportation services. This framework encompasses two stages: adapting road segmentation techniques to extract semantically meaningful atomic spatial units and merging nearby units into larger regions through a spatial clustering process. The authors underscore the importance of temporal predictability in transportation service operations, emphasizing that regions generated with higher predictability can enable more accurate service operation decisions. The RegionGen framework for spatiotemporal transportation service management is a two-step process. First, it segments the city into atomic spatial elements based on road networks and obstacles. Second, it clusters these elements to maximize key operating characteristics through a multi-objective optimization process. Two main challenges in designing such a region generation framework are identified: guaranteeing good spatial semantic meaning and meeting operation requirements of spatiotemporal services. To address these challenges, the authors propose aggregating fine-grained regions into larger ones to acquire better operating characteristics, including predictability, granularity, and specificity. Predictability, which refers to the ease of predicting future events of interest for the service, is quantified using the autocorrelation function, ACF. This model-agnostic and efficient measurement is computed as the ratio of the covariance of the time series at different lags to the variance of the time series. Granularity, measured by the region area, requires a trade-off with predictability. A maximum region area constraint is proposed to meet the need for fine-grained spatial granularity. Specificity, the ratio of service required subareas to the total area of the generated region, is also quantified. The aim is to generate regions that closely match the actual service area, with few redundant parts where no service is required. Extensive experiments on 3 spatiotemporal service datasets verify that RegionGen can generate more suitable regions than traditional methods for spatiotemporal transportation service. This framework has the potential to significantly improve the efficiency and effectiveness of spatiotemporal transportation services. Efficient operation in regions relies heavily on service specificity, which is crucial for optimal resource allocation. To quantify this, the service specificity ratio is introduced, defined as the proportion of service required area to the total area of a region. This ratio is calculated using historical service records and geohash units, allowing for efficient area size calculation. The paper formulates a bi-objective optimization problem, aiming to maximize both specificity and predictability of clustered regions. This involves segmenting atomic spatial elements, clustering them, and ensuring each cluster meets operational requirements. The proposed framework, RegionGen, consists of 2 core components: atomic spatial element segmentation and clustering. The segmentation component extracts atomic spatial elements with good spatial semantic meaning, while the clustering component solves an n-fard problem to maximize predictability and specificity. By optimizing these two objectives, RegionGen enables the creation of efficient and effective regions, leading to improved resource allocation and operational efficiency. The RegionGen framework addresses the challenge of balancing specificity and predictability, providing a novel solution for regional operation optimization. The paper's findings have significant implications for industries relying on regional operations, such as logistics, transportation, and urban planning. The RegionGen framework, illustrated in Figure 2, employs a data-driven approach for spatiotemporal transportation service management. It incorporates a road map segmentation method that integrates obstacle entities, ensuring generated regions do not cross obstacles. This approach involves dilating road segments to remove redundant details, thinning segments to extract their skeletons, and applying connected component labeling to generate road segmentation. The obstacle-aware road map segmentation method incorporates geographic obstacle data, converting it into binary images and fusing it with the thinned road raster. This process yields atomic spatiotemporal elements, denoted as P, which are fine-grained and suitable for operating spatiotemporal services. To filter out unnecessary atomic elements, the framework imposes restrictions based on service data, filtering out elements with data amounts smaller than a specified threshold, alpha. This step reduces the scale of subsequent clustering problems and ensures better spatial granularity for supporting spatiotemporal services. The atomic spatial element clustering process involves transforming the problem into a graph format, where each atomic spatial element is represented as a node, and their edges denote their aggregatable property. Edges are determined based on domain knowledge and geographic constraints, including oversize and already predictable properties, as well as adjacent and obstacle constraints. These constraints ensure that the clustered regions are meaningful for spatiotemporal services. The graph generation process involves atomic spatial elements, where nodes represent 7 elements, and an adjacency matrix is calculated based on geographic distance and obstacle entities. For instance, Figure 4 illustrates how certain elements cannot be merged due to a river and distance, denoted by red and blue dotted lines. To optimize predictability and specificity, the co-optimization process iteratively refines Pareto solutions, as detailed in Figure 5. The algorithm starts with an initial set of solutions and iteratively improves them by moving boundary nodes to achieve better predictability or specificity, while respecting geographic constraints. This process stops when no further positive gains can be obtained or reaches the maximum iteration number. Notably, the time complexity of this co-optimization algorithm is O(n)(E), where E is the edge set of the graph. This setup is part of a larger system, as depicted in Figure 6, which integrates both offline optimization and online query for transportation services. The offline optimization component involves the graph generation and co-optimization processes, while the online query component enables real-time transportation service requests. The proposed RegionGen framework optimizes the generation of regions for spatiotemporal transportation service management, enhancing demand prediction accuracy. Implemented in a real-world setting, RegionGen outperforms baseline methods on 3 datasets: designated driver, freight transport, and taxi demand. The evaluation metrics, including a CF_daily and metrics, consistently favor RegionGen. Additionally, robustness analysis on the Chicago taxi demand dataset using state-of-the-art models further confirms RegionGen's superiority. The system's architecture, presented in Figure 6, comprises offline and online components, with an average response time of 100 milliseconds, making it suitable for real-life deployment. The experiments on designated driver and freight transport datasets, as well as a taxi demand dataset, using the proposed RegionGen method and several baseline methods, have been conducted. The results are presented in Tables 1 and 2, and Figures 7a, d. Table 1 shows that RegionGen achieves the best specificity and results on the designated driver and freight transport datasets, despite having a significantly longer running time compared to the baselines. DBSCAN exhibits a long-tail phenomenon, which may cause inconvenience for operating services in these regions. Figure 7a illustrates the ACF_daily versus recall, where RegionGen consistently achieves the best ACF_daily, demonstrating its robustness. DBSCAN and fixed shape methods, grid and hexagon, perform consistently poorly. Figure 7b analyzes the scalability of RegionGen, showing that as the scale increases, both the running time and the converge epochs of the algorithm increase synchronously. RegionGen can support fine-grained spatiotemporal service in a metropolis like Shanghai, even with 10,000 atomic elements, which takes 17 hours to run. Figure 7c displays the ACF metric of the best predictability solution and the specificity metric of the best specificity solutions from different Pareto solution sets obtained by changing W, the probability of optimizing the predictability objective. The results indicate that with the increase of W, the ACF metric gradually increases and the specificity metric decreases. Figure 7d compares different initialization methods, including D-balance, greedy, and fluid, by generating initial solutions with 30 different random seeds for each method. The results show that the final solutions given by greedy and fluid are quite different with diverse random seeds. Overall, the results demonstrate the effectiveness and scalability of RegionGen in generating high-quality regions for spatiotemporal service management, achieving better performance than the baselines and exhibiting robustness and scalability suitable for realistic deployment. RegionGen, a unified data-driven region generation framework, is designed to adapt to the diverse operation requirements of spatiotemporal services while preserving spatial semantic meaning. This framework initiates by segmenting cities into atomic spatial elements, leveraging fine-grained road networks and obstacle entities. These elements are then aggregated to optimize key operating characteristics, such as predictability and specificity. Experimental results on 3 transportation datasets demonstrate RegionGen's efficacy in generating regions with superior operating characteristics compared to existing baselines at equivalent granularity. Furthermore, demand prediction services conducted on the generated regions validate RegionGen's effectiveness. The RegionGen framework's ability to balance adaptability and spatial semantic meaning makes it an invaluable tool for online transportation platforms seeking to provide intelligent and satisfactory transportation services. By optimizing region generation, RegionGen enables these platforms to better navigate the complexities of spatiotemporal services, ultimately enhancing the overall user experience. This paper presents a comprehensive overview of methodologies and techniques used in spatial temporal data analysis, focusing on traffic flow prediction and transportation demand forecasting. It emphasizes the importance of considering both spatial and temporal aspects in modeling and predicting traffic flow, as well as the role of deep learning models in improving the accuracy of these predictions. Key concepts and techniques discussed include graph partitioning, spatiotemporal graph convolutional networks, and multi-step dependency relation networks. Efficient algorithms for large-scale data processing are also highlighted, along with the use of multimodal transportation recommendation systems to enhance user experience. The paper provides an extensive list of methodologies and techniques, emphasizing their potential applications in various fields such as urban planning, logistics, and public transit systems. It also addresses the challenges and limitations of current approaches, suggesting areas for future research and development. In conclusion, this paper offers a detailed exploration of spatial temporal data analysis in traffic flow prediction and transportation demand forecasting, highlighting the importance of deep learning models and efficient algorithms for accurate predictions and enhanced user experience. Data-driven region generation frameworks are crucial for spatiotemporal transportation service management. These frameworks involve partitioning graphs into balanced connected classes, addressing the modifiable areal unit problem, and utilizing deep learning for traffic prediction. A key challenge in spatiotemporal traffic prediction is achieving generalizability. To this end, metamodeling and an analytic framework can be employed. Public transport planning, trajectory clustering, and the use of geohashes for location-based services also play significant roles in this context. However, uncertainty quantification in deep spatiotemporal forecasting remains a critical issue that needs to be addressed. The supplementary materials provided in this section aim to support the main findings of the research paper. Firstly, Figure 10 illustrates the use of ACF_daily as a proxy for measuring predictability in time series data, demonstrating its validity through the ACF of different time series and their corresponding prediction errors given by STMGCN on the freight transport dataset for 1-hour time slots. This highlights the importance of ACF_daily in understanding predictability. Next, Figure 11 shows how more data samples can lead to more obvious daily regularity, with each data point representing an atomic spatial element in the freight transport dataset. This emphasizes the significance of sufficient data for identifying patterns and trends. The calculation of specificity is then explained, with examples provided in Figure 12. The serviced area and total area are defined, and the service specificity is calculated using an 8-bit geohash. This calculation is crucial for understanding the spatial distribution and coverage of the data. The paper also outlines a multi-objective node swapping algorithm, Algorithm 1, which aims to co-optimize predictability and specificity. The algorithm iterates through a series of steps, including generating feasible solutions, sampling random numbers to select solutions based on predictability or specificity, identifying boundary sets, and updating the best ACF and specificity values. It also removes non-Pareto solutions and returns the Pareto optimal solutions. This algorithm is essential for optimizing the clustering of nodes while maintaining geographic constraints. Additionally, the page includes a function, movable boundary, which identifies nodes that can be moved between clusters without violating geographic constraints. This function is crucial for the node swapping algorithm, as it ensures that the spatial relationships and constraints are maintained during the optimization process. Finally, Table 3 provides statistics for 3 datasets used in the study: designated driver, freight transport, and open taxi. The table details the number of records, time span, and whether the data is publicly accessible. It also includes information about road and river data obtained from OpenStreetMap, including the number of roads and rivers. A data-driven region generation framework, RegionGen, is proposed for spatiotemporal transportation service management. This framework generates regions that capture spatial and temporal patterns of transportation demand, enhancing service allocation efficiency. RegionGen utilizes a novel graph partition technique, considering geographic adjacency and spatiotemporal correlations among demand data points. 3 baselines are introduced for comparison: grid, hexagon, and DBSCAN, BSC, GCSC, and fluid. These baselines evaluate RegionGen's performance in terms of predictability and specificity. The study employs 3 datasets: designated driver dataset, freight transport dataset, and open taxi dataset, each containing records of transportation service orders with start times and locations. In the experimental setting, road and obstacle vectors are converted into a binary raster, and atomic elements with high ACF_daily or large areas are considered separate nodes in the graph. Geographic adjacent distance and maximum area constraint are set to 50 meters and 5 square kilometers, respectively. For spatiotemporal prediction, the last 10% of each dataset is used as test data, and the previous 10% as validation data. 3 state-of-the-art predictive models STMGCN, ST-Meta, and GraphWaveNet are applied, with hyperparameters fine-tuned by grid search. Initialization methods like D-balance and greedy are discussed. D-balance uses a fast solver to minimize edgecut while tolerating a 5% unbalance, whereas greedy uses a greedy strategy to guide node growth and optimize objectives like predictability and specificity. Fluid, a community detection technique, considers how fluids interact and change size in their environment. RegionGen demonstrates effectiveness in enhancing service allocation efficiency compared to existing baselines, presenting a novel framework for generating regions that capture spatiotemporal patterns of transportation demand.